Who invented time? At some point today, you checked the time. Maybe it was when you woke up, when you left for work, or when you realized you were running late. You looked at a number and immediately understood what it meant. But that number is not something nature created. There are no hours written across the sky, no minutes hidden inside the earth, no universal clock hanging somewhere in space. Humans created the system that divides the day into 24 hours. We named the months, organized the year, synchronized our clocks, and divided the planet into time zones. And none of it happened all at once. The system controlling when we wake up, work, eat, travel, and sleep was assembled over thousands of years by farmers, priests, astronomers, inventors, sailors, and railroad companies. So how did watching the sun cross the sky eventually lead to atomic clocks precise enough to guide satellites? And who decided what time it is? This is the Atlas Guide. For most of human history, nobody needed to know that it was exactly 7:43 in the morning. People organized their lives around events rather than numbers. They woke when the sun rose. They planted when the seasons changed. They rested when darkness arrived. The earliest forms of timekeeping were not clocks. They were patterns in nature. Day followed night. The moon grew full and then disappeared. Winter eventually gave way to spring. These repeating cycles allowed humans to predict what would happen next. Knowing when winter was approaching could mean the difference between having enough food and starving. Tracking the seasons helped farmers decide when to plant. Following the moon helped communities organize ceremonies, journeys, and gatherings. Timekeeping began not because humans were obsessed with punctuality, but because they wanted to survive. As settlements grew into cities, however, saying, "when the sun is high" was no longer enough. Societies needed a way to track not only the passing of a day, but the passing of an entire year. And so they created calendars. Some civilizations built calendars around the moon. A complete cycle of lunar phases lasts roughly 1 month, making it an obvious natural calendar. But 12 lunar cycles do not perfectly match the solar year. Without occasional adjustments, a lunar calendar gradually moves through the seasons. Other societies focused more heavily on the sun. Ancient Egypt developed one of the earliest known calendars, containing 365 days. The year was divided into 12 months of 30 days, followed by 5 additional days. It was practical, but not perfect. Because it was slightly shorter than the true solar year, the calendar slowly drifted away from the seasons. Calendars helped humans locate themselves within the year, but people still needed to divide the individual day. For that, they looked upward. The ancient Egyptians were among the earliest people known to divide daylight into smaller sections. Obelisks and other devices cast shadows that moved as the sun crossed the sky. By watching those shadows, people could separate morning from afternoon and identify different points during the day. Over time, Egyptian systems divided daylight and darkness into groups of 12. That tradition became one of the foundations of the 24-hour day. But ancient hours were not fixed like ours. A summer day contains more daylight than a winter day. If daylight was always divided into 12 parts, then a daytime hour in summer was longer than one in winter. The hours stretched and shrank with the seasons. Today, we think of an hour as an unchanging unit. 60 minutes are always 60 minutes. But why 60? Why not 100? That part of the story leads back to ancient Mesopotamia. Babylonian astronomers used a mathematical system based on the number 60. 60 was useful because it could be divided evenly by many smaller numbers, making it practical for calculations involving astronomy, geometry, and fractions. That base 60 system survived through later mathematics and astronomy. Its legacy remains every time we divide an hour into 60 minutes, a minute into 60 seconds, or a circle into 360 degrees. But shadows had an obvious weakness. Sundials did not work at night or on cloudy days. Humans needed something more reliable. They turned to water. A water clock allowed water to flow gradually into or out of a container. Marks inside showed how much time had passed as the water level changed. Water clocks could operate indoors and after sunset. They appeared in temples, homes, and courtrooms, where they could even limit how long someone was allowed to speak. They were useful, but not especially accurate. Temperature, pressure, and the shape of the container could change how quickly the water flowed. Still, water clocks introduced an important idea. A clock did not have to follow the sky directly. It only needed a process that moved at a predictable rate. Over time, humans experimented with candles, incense, and hourglasses. But the clock, as we recognize it, did not appear until the Middle Ages. During the 14th century, large mechanical clocks began appearing in European towers. These machines were powered by hanging weights and controlled by gears. Many did not have minute hands. Some did not even have visible faces. Their main purpose was to ring bells. The sound told an entire town when to pray, open the market, begin work, close the gates, or return home. This marked an important change. Earlier timekeeping helped people observe the passing day. Mechanical clocks began controlling the day. For the first time, a machine could place an entire community on the same schedule. These early clocks were not very accurate. Some gained or lost around 15 minutes in a single day. That was acceptable when people only needed to know the general hour. But as science, trade, and navigation expanded, greater accuracy became essential. In 1656, Dutch scientist Christian Huygens built the first successful pendulum clock. A pendulum swings at a regular rhythm. By using that rhythm to control a clock's gears, Huygens created a machine far more accurate than most earlier designs. That improved precision soon helped address one of navigation's greatest problems: finding longitude at sea. Sailors could calculate latitude, their position north or south, by observing the sun and stars. Longitude, their position east or west, was much harder. To calculate it, sailors needed to compare the local time aboard their ship with the time at a known location back home. The Earth rotates through 360 degrees in about 24 hours. That means a 1-hour difference represents roughly 15 degrees of longitude. The idea was simple. Building a clock accurate enough to survive an ocean voyage was not. Pendulum clocks struggled on moving ships. Waves, humidity, temperature changes, and constant motion disrupted them. During the 18th century, English clockmaker John Harrison spent decades developing marine timekeepers that could remain accurate at sea. His chronometers helped sailors calculate longitude far more reliably. Accurate clocks were no longer simply convenient. They had become tools of navigation, exploration, and trade. But another problem remained. Different towns still disagreed about what time it was. Before standardized time, most communities used local solar time. Noon occurred when the sun reached its highest point in that town's sky. Because that happened at different moments as you traveled east or west, neighboring towns could have clocks set several minutes apart. For most of history, that did not matter. Then came the railroad. Trains moved quickly between cities. Railroad companies needed coordinated schedules, and a difference of several minutes could confuse passengers or create serious safety risks. Instead of every town setting its clocks according to the sun, entire regions began following one shared time. Britain's railways increasingly adopted Greenwich Mean Time during the 19th century. North American railroads faced the same problem. On November 18, 1883, railroad companies introduced standardized time zones across the United States and Canada. People who had spent their lives following local solar time were suddenly expected to follow time chosen by railroad schedules. To some critics, it seemed as though railroad companies had taken control of time itself. But standardized time was too useful to reject. It made transportation safer, schedules clearer, and communication easier. Time was no longer determined only by the sun above your town. It had become a large-scale agreement. By the 20th century, mechanical clocks had become extremely sophisticated, but gears and pendulums were still affected by friction, temperature, and wear. Scientists needed something more stable. In 1927, engineer Warren Marrison developed a clock regulated by the vibrations of a quartz crystal. When electricity is applied to quartz, the crystal vibrates at a highly regular frequency. By counting those vibrations, quartz clocks could measure time more consistently than most mechanical clocks. Eventually, inexpensive quartz watches brought accurate timekeeping to millions of people. But scientists continued searching for an even more dependable rhythm. They found one inside the atom. Atoms of the same element respond to electromagnetic radiation at extremely consistent frequencies. Unlike a pendulum, an atom does not wear down. It has no gears and needs no oil. In 1967, the international definition of the second was based on the cesium-133 atom. Today, 1 second is defined by counting exactly 9,192,631,770 cycles associated with a specific transition inside cesium-133. We no longer define the second simply by dividing the Earth's day. We define it by counting the behavior of atoms. That precision affects far more than the clock on your wall. Communication networks use precise timing to organize signals. Electrical grids use it to coordinate power. Financial systems use it to determine the exact order of transactions. And GPS satellites use atomic clocks to help determine your location. The satellites transmit carefully timed signals toward Earth. Your phone measures how long those signals took to arrive and compares signals from several satellites. Even a tiny timing error could produce a major error in position. GPS must also account for Einstein's theory of relativity. Because satellites move quickly and experience weaker gravity than clocks on Earth, their clocks tick at a slightly different rate. Without correcting for that difference, GPS locations would steadily drift away from their true positions. The device telling you where to turn at the next intersection depends on thousands of years of timekeeping. We began by watching shadows. Now we measure billions of atomic cycles every second. So, who invented time? Nobody did. Time passed before humans existed, and it would continue passing if every clock disappeared tomorrow. What humans invented was a way to divide time. Then we created tools to measure those divisions. Finally, we agreed to share them. Calendars grew from the cycles of the sun, moon, and seasons. Ancient mathematics gave us 60-minute hours. Water clocks carried time through the night. Mechanical clocks placed cities on schedules. Marine chronometers guided ships across oceans. Railroads created standardized time zones. Quartz crystals made accurate timekeeping widely available. Atomic clocks turned the second into one of the most precisely measured units in existence. And somewhere along the way, timekeeping changed from a tool humans used into a system that organizes human life. We wake at certain times. We work for a certain number of hours. We celebrate birthdays and anniversaries. We count deadlines. Every appointment, alarm, calendar, and countdown rests on an agreement built by civilizations separated by thousands of years. So the next time you look at a clock, remember this. You are not actually seeing time. You are seeing humanity's best attempt to count it. This is the Atlas Guide. Thanks for watching, and we look forward to seeing you in the next episode.